Hello, welcome to my solution of day 17 of Advent of Code 2024. It was a really involved problem today. Involved reverse engineering of an assembly program. Basically, you had a program containing 8 assembly instructions, which were given in the description. And those instructions could get or all get an operand, which is either a combo operand or a literal operand. In case it is a literal, it would just take the value as is. And in case it would be a combo operand, it would either be a literal if it was less than or equal to 3, or it would be one of the other registers of the program. And there were 3 memory registers, A, B, and C. So 3 places to store something in memory. Now the first part was basically to code out all these assembly instructions and to ensure that your program ran correctly. But the real difficulty was in the second part, where you had to find a certain input value for your program such that it gave a certain output. Now instead of coding this all out, I want to go straight into the disassembly of the program, because that's what you will need to fix this problem. So looking at my input, my program, it's fairly short, and my assumption is that everybody has the same program except for the literals in this program. So there's a couple of instructions in here which have a literal operand, and I think those will differ depending on your input. But I think the rest of the instructions will most likely be the same. I'm not sure about that. However, the program contains, I think, 8 instructions. Is that correct? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And I basically decoded them here. So the first instruction is a BST instruction, which will do take some combo operand, which in our case is the value of register A, and it will perform a modulo 8 operation on it. Now modulo 8 is the same as doing a bitwise AND with 7, because you just take the 3 least significant bits of the value. So the first instruction would be B is A bitwise AND with 7. Now the second instruction is performing an XOR. It's doing the BXL instruction, and it's taking a literal operand, which in our case is 2. So in our case, B becomes B XOR 2. Third instruction is the CDV instruction, which performs a division. And the division is really nothing more than a right shift if you look at it carefully, because you're raising 2 to the power of the operand and you're dividing by that. Now what that means is that you're basically right shifting the value of A B times. So all of these operations are really bitwise operations that you're performing. That's the first insight you can make about this program. So this sets the register C to the value of A right shifted B times. Then the fourth operation performs an XOR with the literal value again. It's setting B to B XOR 3. The fifth operation does the same, but then between 2 registers, B and C. And then you get an output operation. Now there's only one output per loop. And this output that's recorded is the value of B, again modulo 8. So we can again do this AND 7 trick to get the output. And then the value of A is set to a different value, taking as input the old A and dividing it by 8. So that's effectively also a right shift by 3 bits. So and then the last instruction is a jump, which takes the value of 0, which will mean that the jump will occur if A is not 0, so it will jump back to the first instruction. But if A is 0, it will exit the program. So what this means is basically your program is a function with one input and two outputs. The first output is the next A, and the second output is the output it sent to the output stream, basically. That's how you can view your program. Now another insight we can make about this program is that looking at the exit of the program, like I said, the output value of A has to be 0, which would mean that A before right shifting should be at most 7. Why is that? Because we're right shifting 3 times, so any bit beyond the 3 least significant bits of A has to be 0 for the program to exit. Okay. Now let's first look at what the problem is in part B of the puzzle. So the question is, can you find an input value for a program such that the output of the program will be the list of instructions which forms the program? So in our case, the output of our program should be exactly this sequence of integers, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 integers. Now if you look carefully at the program, you see that all these operations act on 3 bits. All these bitwise operations, because we're doing an AND with 7 a lot of times, and this means that only the least significant 3 bits of the value are important. The exception is this instruction right here, where we're shifting the value of A, and this right shift, the B, can be at most 7. So that would mean that we use at most 10 bits of A for this operation. Okay. And what I'm going to do is I'm going to try to solve this problem recursively by working my way back towards the front. So as I noted before already, I know how to exit the program because A1, so the input value has to be 0, output value has to be 0 at some point. And the input value A at that iteration has to be at most 7. So if I'm going to write a function, and this function would call my program, my decompiled program, I know for sure that at the last iteration the only valid values would be 0 until 7. Or until is excluding 8, so it will be up until 7. So any of these values have to give the value of 0. Now let's see what it actually produces. I'm going to run a program. So looking at this output, so the first value is A1. We see that all the outputs are actually 0. But another constraint is, of course, that this value needs to match the instruction value at that point. And we see that for I is 1, that gave the right result. So here we have to have a check that, so let's call this our output. And we have an, let me see. We have an output and an instruction output. and the instruction output needs to be the same as our instruction at that point, right? So we're going to take our instructions as input. And we're going to have to know our instruction at this index. So we need some instruction index. And our instruction will be the instruction at that index. And this has to be true. And in this case, I also need to check that output has to be 0, of course. And now there should be only one value, which is 1. Oh, I forgot to get my instructions, of course. To int. Program 2, oh, I forgot to strip program. Let me see. Okay. So how to do this recursively then? And for this I'm going to create a queue which will have our states. And the state will be the index of the instruction that we're processing and the expected output of that instruction. And we know that our first, so starting from the back up to the front, we know for sure that the first output needs to be 0 and the index will be at the end of the list. So we're starting off with this instruction. Instructions.size to 0, which will exit the program. This is our expected output. Now I'm putting instruction size here because I'm going to decrement before I'm going to iterate on the instruction. So I'm going to do this in a loop. While pending is not empty, I'm taking the next state, expected output, and the next index will be index -1. So we're going to start off with the last index because we're starting off with the instruction.size. And we have to exit this if our index equals 0. Then we actually found the correct value. To do handle the correct value we found. Now I'm going to process all these bits inside here. I'm going to take the instruction belonging to this index and I have to convert this to long here. And the output has to be not 0, but it has to be the expected output, which for our first state will be 0, of course. But we will modify the expected output to the input that we got at this step, because that input will yield that expected output at the next step. So if we found a candidate here, we're going to add a state to our pending queue. And this index will be the next index to I. And I don't think I'm forgetting I think I'm forgetting something here, because of course I need to left shift the value first and adding I here. So what I forget here is that the value we're processing here is the value for this step. I'm looking for an input value that yields the expected output value. But as input value, I'm going to left shift the previous expected output and only modify the least significant bits, because the program will eventually, on each step, divide the expected output by 8, so it will right shift this value. So in this loop I need to do the opposite, if that makes any sense. Maybe that's a little bit complicated. Now here we're going to keep a list of states or values we found, valid values, and we're going to add them here if we found them. And then finally we would have to take the minimum of those values, right? Should be OR, of course. So I'm taking the previous expected output, left shifting it 3, and modifying the 3 least significant bits by iterating from 0 to 8. And this way I'm building my value up 3 bits at a time, basically. I'm only manipulating at least 3 significant bits every time. And I'm checking this value as input and whether it matches the expected output. If that's true, and the instruction output also matches, then this is a valid candidate and I can add it to the list of next candidates to process, where the index will be 1 less than the previous iteration, right? So let's see what this will output. Obviously I made a mistake here. Of course I need to stop when I found a valid value. Oh, I should take the next value. Okay, so this gives an answer. Now of course we can I will also print all the other candidates, so you see there are actually more. One, two, three, four, five, six, seven, 8 valid values. And if I return this list, I can check for each of those values that they are actually correct. And we're going to run the program. I'm going to call that run complete, or just call it program. Input, and it just will return a list of integers. Now we'll take a is input, and while a is not 0, because that will exit our program, we're gonna run our decompiled program with a as input, and that will give two outputs, a1 and out, and we're gonna add out to the results. And we're gonna take a1 as next a. To int. Require that a program of our result equals the instructions. I see that this was true for every instruction. If you don't believe me, I can also print it. They will give the valid result. So our actual result is the minimum of those values. Which is this answer right here. Now this runs a very minimal amount of iterations. If you keep track of the number of iterations that it actually runs, 0. For every invocation of our program, we will increment this value here. So that's here. So it only runs 1432 iterations. And that's for an integer that can take up to 48 bits. So if you think about it, 2 to the power of 48 is somewhere, I can do the calculation, but it's at least 1 trillion values. It's more, I think, than that. But out of those trillion values, only like a handful of values are actually candidates. So this runs within a few milliseconds. So that's basically it. That's how you approach this problem and reach a solution. Hope to see you next time. Bye bye.